Good morning, everyone. So this is my second talk in this conference. So I guess everyone was here for the first one, so maybe I don't have to say again that I'm Serge Stinckwich. I'm working in an international joint research unit, and my research unit is working mostly on modeling and simulation of complex systems. And this is why I was really interested to have something to do computational and to do math and science and Smalltalk. And this is why I started this project, I don't remember exactly, maybe 5 or 6 years ago. And there was nothing, not exactly, there was a lot of code, but all the code was a little bit dispersed between different contributors, and there was no way to do mathematics very easily with this code. So I decided to try to put everything in the same code base. And recently we have a big milestone because we are now at the 1.0 version. So it's not only my project, there is lots of contributors and more since last year. So basically this is the same presentation I've done in ESUG, last ESUG. I had some slides because there was some, we had some features since the last ESUG. First of all, just want to say that I'm not a mathematician. I'm working with mathematicians. I'm using a lot of math, but I'm basically a computer scientist. So I'm, from time to time, maybe I will do some mistakes. Okay. So, first of all, I want to just explain what is PolyMath and what is the current status of this software. So, this is PolyMath is a computational framework, a numerical framework for Pharo, and it's written in pure Pharo. So it means that at the moment the performance are not really great, but maybe in the future we will try to reconsider this point. There are lots of existing code, and I will show you some demos later. And you have ordinary differential equation, you can manipulate random number generators. You have lots of algorithms about linear algebra, etc., etc. So there are already a good code base compared to what existing framework in Python. I don't know exactly how much, how far we are from, for example, a framework like SciPy, but we are not ridiculous. And recently, we had support for tabular data analysis. So this was done during the GSOC by a student called Olekskandr. And this is now part of PolyMath. Because more and more the people, they want to do something similar to what they do in Python, for example, in Pandas. And they want to be able to analyze data available in tabular format. So this is the this is open source. This is MIT license. We released during ESUG the 1.0 version, and all the code is available here on GitHub. First of all, I really want to thank these guys because they are the main contributors of the software, and we are looking for more people because it's a very big project, and I know that some of the algorithms that we want to implement are sometimes very complex, and you need a lot of expertise in mathematics to implement them correctly. So if you are interested by having something similar to framework in Python, please contribute. All contributions are valuable, not only code, but also documentation. And we try to spend a lot of time also on documentation. We have regular meetings on Discord, on the Discord channel, so the PolyMath channel, sorry. Just to say a few words about these guys. So Olek is the main developer behind DataFrame. Conrad we have developed with Conrad a new software based on PolyMath called Active Papers that allows the people to do reproducible research framework. Emal is a guy located in London, I never met him just on the Discord channel, but he's very active, and he has done a lot of cleaning. This is very important because the code of this software has been done by a lot of different people with a lot of there are a lot of cultural difference between them. Though, so we need a lot of cleanings in order to use this code. And the two last guys, they are Indian guys, Atharva and Nikhil, and they have participated to the PolyMath development during their last GSOC, so Google Summer of Code. And especially Atharva has done incredible work. He adds some codes to do PCA and t-SNE that are very famous visualization algorithm for machine learning. Okay, so please join if you're interested. We are looking for more people. So recently what we have done, so we released a 1.0 version, and we have now a logo. So we have done a lot of cleaning. We had a lot of unit tests. I don't know, where is the doctor here? Ah, the doctor is here. Thank you. We need the doctor. Already mentioned that we have worked on machine learning and tools like PCA or t-SNE. Emal cleaned the random numbers. I have done also a lot of cleaning in the package about automatic differentiation. This package has not been done by me, but someone else. And I was interested because automatic differentiation is the name. In fact, the people from machine learning, the people who are doing neural networks, they just reinvent automatic differentiation. This is, so it happens sometimes. So this is very important to have something like that when you want to do machine learning. I will show you a demo later. Okay, so we had a lot of things. We have a contributing guide. And since the 1.0 version, we have a trunk-based development. That means that everything happens in the master branch, and we just have one release branch from time to time. Okay, so the release branch is the stable one that you should use. And the trunk, the master branch, is the one that maybe the code there could break inside this branch. Okay, some metrics about the code. So it's 24,000 lines of codes, more than 300 classes. We have a lot of tests. So yeah, we try to add more and more tests, and we try to also to do TDD also, because we try to redesign the API of the software by using TDD. We have TDD session to do that, and we have lots of. The project is quite popular on GitHub among the Pharo projects. So. So it's based on Pharo. I just want to explain a little bit the logo. Maybe you see on the first slide the logo that we choose, and just to explain the story behind the logo. So you have Pharo. Inside the O of Pharo, you have the lighthouse. And on top of this lighthouse, you have the light. And usually the light is amplified by what is called a Fresnel's lens. Okay? Fresnel is the name of the guy who invented this kind of lens. And this is quite similar to plateau solids also. And so we decided to try to mix all these ideas together. I don't know if it was a good idea or not, but yeah. So this is the logo. So basically this is the light on top of the lighthouse. So it has been designed by Lucy Dolia, who is doing all the logo of the ISE conference. And we use the square bracket just to remember that we are in Smalltalk. Okay. The code is mainly done in Pharo, but this is completely portable, I guess. So if people are interested to have a port on Quiz, on Squeak, Visual Age, something else, we will be really happy to help these ports. So demos. because I can explain a lot about what is inside the software, but I think it's better to have demos. So I have demos that I've done 2 years ago in Hessug. I hope that there will be not too much people that would be boring because I would do the same demos, and I have new demos that I have done during the last Hessug. So the first one will be how to compute pi. So you know pi. And I will use this algorithm. It's called the Brent-Salamine algorithm. I don't want to explain the details. I don't know exactly the details. I just copy-paste the algorithm here. And apparently it's not too bad algorithm. The convergence is quite fast. So you can approximate pi by computing these series of numbers, an and bn and tn. And you have the code here. And what is interesting in PolyMath is that we are supporting arbitrary precision float numbers. Okay, so in Pharo and in other Smalltalk, you have float numbers that are IEEE numbers, so they are quite limited. And here you can choose the number of bits that you can use to represent floats. Okay, so I will do the demo live. Yeah. Okay, this one. So this is the code we just see. So here I will choose the number of bits. You see here. Is it readable for everyone? Okay, this is the number of bits. So I will try to do the first experiment with this number of bits. So yeah, you see here the value of pi, 3.14, etc. So here we use 10 bits to represent the number. And if I increase the number of bits, we will have a better precision. So I can jump to 50 bits, for example. And I can do, yeah. So you see the numbers. The precision is much more important. And I can do the same, I don't know, I can say 1,000 bit, yeah. And you see, yeah, a very accurate number here with lots of decimals. So this is part of so we have a class to represent this kind of numbers. You just have to choose the number of bits, and you can do the usual computation. You can do addition, multiplication between these numbers. This is the power of polymorphism. So it's very, and we have a project also, because here you have to choose the number of bits, and we have a project also, but it's not done at the moment. We have done some experiment, but it's not available for production. The idea is not to choose the number of bits, but the number of bits will be chosen depending of what the operation you are doing. Okay. Go back to the presentation. Just want to introduce this very nice polynomial. So you see, this is a function, y, that depends of a and b. Okay, so nothing fancy about that. And I will set up the value of a and b, and we try to compute the value of these polynomials. Okay? So we have some code to do that. Yeah. So this is the code. And here I'm not using PolyMath. I'm just using the basic Smalltalk. I build a function, a block of x and y, and I compute the values when a is this value and b is this value, and I obtain a result that is 1.17. Okay, let's try on the inside Pharo. Okay, I have to copy paste the code. Problem, I don't have the code. Yeah, I forget to. So maybe I will do it by by hand. This one? Yeah, but yeah. Maybe I put the code in comments. Where should I? Don't remember how to view the comments. Comments? No. In the history of the playground. Ah, thank you. No, it's not this one. Okay, do we have time? Yeah, I'm not in front of people. Yeah, it's always difficult. So it's a function of x and y. So in fact, this is a and b. 2, 3. I think I have the code somewhere, but I don't know exactly. I don't want to spend too much time on that. Yeah, plus x raised to multiply by 11 multiplied by x raised to y raised to minus 100, multiplied by x raised. I need a doctor. Okay, it's almost done. Yeah, raised to 8 plus x on 2 multiplied by y. Okay. Okay, it was not that difficult. And I want to compute the value of the function when yeah, I have a typo somewhere. Where is the typo? Okay, thank you. Yeah, another one? No, it's okay. And 2, 3, 0, 6. Okay, yeah, let's try. Yeah, thank you. So this is the answer. Okay, you can read it. 1.17, etc. And okay, what do you think about that? No? Go back to my presentation. In fact, this is not the correct answer. The exact result is minus 0.82. So it's completely different numbers. So you see here, with this very, very special polynomials, it's called rump polynomials, that have been built in order to produce approximation errors inside at the end of the computation. And so what we can try to do is to promise I don't have the code. If you use maybe I can do it later for the people who are interested to see this demo, this part of the demo. But if you use numbers that like the one that we used before, this is possible to have the correct answer, in fact. And what is really funny with this kind of examples is that if you change by hand the precision of your number, okay, you increase a little bit the precision, 40 bits by 50 bits. The value that you will obtain will be completely random, in fact, completely different. And you have to put a lot of bits, don't remember exactly, but more than 200 bits, maybe 300 bits, in order to have this correct result. So you need to know exactly, sometimes, the number of bits in order to do the correct computation. Yeah, sure.
What happens if you use fraction?
Yeah, I have understood the question. Yeah, what happens when you use a fraction? I don't know, I didn't try, but can try later.
But is this faster than using fractions? Have you compared? Because
no, and I have no benchmark for this. Yeah.
Okay. Okay.
I don't know. I guess the fraction will be very big here because you have. Yeah. So yeah, I don't know. I have to check. Okay. Another example I want to show you is that this is this one. We support ordinary differential equations, okay? And we can solve ordinary differential equations. We have, I don't remember exactly, but we have lots of different solver, including the one that is the one that everyone is using. It's called Runge-Kutta 4. It's the most basic solver for ordinary differential equations. So here you have an ordinary differential equations. So it's 3 equations here, and I want to solve it, and I want to print the results. And okay, this is the quite famous. It's the Lorentz attractor. It's a kind of chaotic systems that you can find in physics or in biology. And so it's when you solve this equation, you can print the result. Here we are using Russell 2 to do that. So you see, we have lots of things, existing things inside PolyMath. Let's try to do more complex math now. It's okay for the math for everyone here? Lorentz attractor. So DataFrame. I have no time to explain all the details about DataFrame, but basically DataFrame is an extension of PolyMath that allows you to do data analysis on tabular data. So here we have a separate repository. So you can build data like that with row and columns, and you can after that do operation on this kind of data. You can select some columns depending on some values, etc. This is quite similar to what you can do with a relational database. In fact, you have operation to do selection on the rows and the columns. And I will just show you how it works on a small demo. So just have to find the demo. Yeah, DataFrame. So I have done this demo yesterday night, and in fact, yesterday in Russell 3, they just had the support for doing charts. There was no support in Russell 3 to do charts and graphs, so they just added. Alexandre just added yesterday, and Olek has done a small demo about using data, and so here we will use DataFrame, and we will try to use a linear regression in order to visualize the data. Okay, so here I'm loading a data set. This one. This is a table of with lots of rows. If I remember, there is something like 14 rows, and you have 506 different items, and each of these items is represent the price of houses in some district of Boston. Okay, so you have one house with the price of the house and other information. I will just use, in fact, 2 columns, the columns of the number of the room of each house, okay, and the number that is the price of the house, okay, and I will try to understand if there is some relationship between the number of rooms and the price, okay. So in order to do that, we don't need a very elaborate machine learning stuff. We just need the basic algorithm that everyone knows here. This is linear regression. So we try to put everything on the line, and after that we will try to plot So here I'm using the new RS chart class of the Russell 3. And if I execute, you see that apparently most of the houses in Boston, they follow this kind of regression. So here we compute the, with the PM linear regression, we have compute the slope of the line and the intercept of the line. Okay, so this is something that is very easy to do for data analysis, and this is part of PolyMath, and we have also regression analysis, more elaborate one. We have, for example, PCA. I will do PCA demo later. And here I'm using Russell 3, so this is the new support, because in Russell 2 there was some support to plot charts and plot graph, and this is new since yesterday. So this is the just-in-time presentation. Okay, next, let's try to do some differentiation now. I don't know if I have time. Yeah, still have time. So differentiation. Who knows what is differentiation? A little bit. If you have done some math at the university, maybe at the first year, this is something quite common. So just a few information about that. So the derivatives of a function, of a single variable, so we keep it simple here, we just talk about single variable. So this is called f prime x. So this is the rate at which the value of f changes at x. Okay, so basically, if you want to represent this in the visualization, this is just the slope at this point. So you have this function f, black here, and you have lines here, and this is the derivative. This is the slope of the curve at this point. Okay, so this is the function. If you compute this for all x, you compute the derivative functions, in fact, and you can compute the function like that. This is the difference of f of x over the difference of x, okay? So this is what we have learned at the university. And you have different ways to compute that. In fact, the basic idea is that you try to find a very a difference of x that I will call h here, the minimum possible. And so theoretically, the smaller the h is, the better the result will be. Okay. So you have different variation of this. You can do backward difference, you can do central difference, you can do forward difference. Okay, this is just a detail, but in fact, this doesn't work. If you, this is something that we have learned at school or at university, but it doesn't work if you want to compute this with a computer, okay? Because it's very difficult to find a good h, and for very small value of h, in fact, you will have some errors, so very similar to the errors that we have seen in the Rumps polynomials, and you will have something like that. Okay, this is the code. I want to see this one. So you will have something like that. So here I just visualize the value of h, the step, okay? And here you have the relative error. So at the beginning, it's okay. You decrease the value of h. We are taking the blue lines, for example. You take the blue line, so you compute the difference of f over difference of x. And everything is okay. And after a while, okay, you arrive at around 10 minus, at the power of minus 8, something like that. In fact, the error grows. Instead of having something that will continue to decrease, the error grows. And because, in fact, there are some cancellation errors, because you are doing subtraction. And due to the limited number of bits that you use for representing numbers, even if you use arbitrary float representation, you will have this kind of problems. This kind of problems maybe will happen later. with the step that is will be less than this one, but you will have the same problem, okay? So usually we don't use this kind of algorithm to compute the derivatives. Okay, so let's try this one. Okay. Yeah. So what I am doing here, I want to compute the derivative of f of x that is sinus x, and I want to compute it at when x is 0.5. Okay, so I have here I compute the difference. Okay, you see, and I want to print the error, so I just do the difference between I know that the derivative of sinus x is cosinus x. Okay, so I compute the difference, and I will print here the error. Okay, so normally if you decrease the value of h, okay, you see the value of the error decrease, but yeah, okay, I can do something like that and decrease, but normally after a while, that doesn't work. Yeah, so you see, after a while, the error is no more decreasing, but it will increase. So this is a real problem. Okay. So how you can solve this kind of problems? So the people, they introduce other ways to do differentiation. I will just talk about two ways to avoid this kind of problems. What you can do is to do complex step method. So instead of using floats, you use complex number. And if you use complex numbers, in fact, you can avoid the subtractive errors, the cancellation errors. Because if you do the math, okay, you compute f of x plus, so f of a complex number, okay, and in fact you have two numbers, a real value and a complex number, and something that will goes to 0, okay, so at the end you can compute f prime of x, or the derivative of x, like that. So this is the imaginary part of this value, okay, so this is very easy to compute, it's f of x, divided by h, and something that will go to 0 when you increase the value of h. So in fact, you can compute the derivatives with the complex methods much more easily than with you will avoid, in fact, all the problems of cancellation, like the one that we see before, okay? So this is how it works. So I want to compute the derivative of sinus x squared, okay, at the value of pi over 2, okay? So I can do it like that, just copy-paste the code, and I will print, okay, so you have the result here. And in fact, you obtain two results. You obtain the value, in fact, with one computation, you obtain the value of f and the derivative of f, okay? And, okay, if you print the errors, go back to the slides. If you print the errors, this is the green line, and you see that this is much better than the other one, because after a while, so the errors decrease, and after a while the errors is stable. Okay, so you avoid completely the problem that you have with the basic algorithm. So we have this inside PolyMath, and we have also something more elaborate called automatic differentiation. And the idea of automatic differentiation, and this is what the people are using in neural networks, is that they want to compute a function, and they want also to compute the derivative of a function. And the function can be a general program, not only a mathematical function, but also a general program. So how to compute derivatives of general programs? In fact, you have a theory behind called dual numbers. So dual numbers are very similar to complex numbers, The only difference is that when you multiply, so this is dual numbers, a plus b epsilon, okay? So it's very similar to complex number, except you have epsilon instead of I. When you multiply 2 epsilon, so when you multiply 2I, you obtain -1, okay? When you multiply 2 epsilon, you obtain 0, okay? So you can build an algebra on top of that. And what is really interesting is that you can use these numbers to compute very accurate derivation of differentiation of general program. So this is one example. So if I want to, so I want to compute the derivatives of this function f, okay, quite complex. So I have this code, and I just create a dual number. So it's PM dual number because we prefix all the PolyMath class with PM, okay, PolyMath. And we start with a number. We want to compute the derivative at this value, and we put 1 as epsilon. And in fact, we will be able to compute at the same time the derivatives and the value of the function at this point. Okay, so you see here that the derivatives is 4.05, and if you know the derivatives of functions, this is this one. You know because you use, I don't know what, Mathematica or something like that to compute the symbolic the differentiation, you will obtain almost the same result, okay? So at the moment we support, there are different ways to compute, to do automatic differentiation. At the moment we only support forward methods, but there are also backward methods that are more interesting for neural networks. So we want to implement them. So in order to use this kind of automatic differentiation in machine learning later. Okay. Okay. So this is my. We jump to another demo. So I just want to talk about dimensionality reduction. So I don't know if you know about that, how it works. Skip something. So sometimes you have, I need a piece of paper or something like that. Someone has a piece of paper. I will, just for my, yeah, I can do whatever I want. Just one piece is okay. So, okay, so sometimes you have, you remember the data set that we have seen before, the Boston data set? There are lots of dimensions, 14 dimensions, so it's very difficult to understand this data set. So the people, most of the time, they want to reduce the data set. Okay, and this is the same for neural networks. You have neural networks with hundreds of neurons, and the inputs and the outputs are also they are using tensors, so the tensors can also have lots of dimensions. So the dimensionality reduction is the process of reducing the number of variables in order to understand better the data set. Okay? So there are many ways to do that. So for example, here you have something very simple. You have something like that. Okay, so this is in 3 dimensions. You project in 2 dimensions, and maybe on 1 dimension, and maybe you can find some patterns interesting in your data sets. Okay, so I will show you here two ways to do dimensionality reduction. So the first one is PCA. Who knows about PCA? Very, very simple ways to solve this problem of dimensionality curves. So this is used in machine learning, so it's a statistical way to do that. So basically, you have something that is in an n dimension space, and you want to project everything on 2 dimensions. Okay, so you do a projection, so you have a very complex data set that is in n dimensions, and you find a way to project it into 3 dimensions or 2 dimensions. Okay, And the idea is to perform a linear mapping of the data, and you want to maximize the variance in order to see what is the patterns that is interesting, okay? So, yeah, so this is a visualization of what the people are doing. So, for example, you have these data sets, and you find, in fact, the maximal variance here. You see, you have the maximum of variance here, and after that, you can find another dimension where there is lots of variance, okay? And you project all the data on these two axes, okay? So basically, this is just a projection, okay, a linear projection. So when two items of this data set are close together, they will be close together on the projection, okay? So this is why we call it linear. There is no transformation of in terms of, there is no spatial transformation of these items. Okay, so let's try to do it on the computer. Yeah, PCA demo. So here I'm using another data set called the iris data set. So I'm using also DataFrame. So the iris data set is quite well known. It's the data set of flowers and iris flowers with different spaces, and inside this data set you can find the length of the petal. So you can find for each flower you can find some characteristic of this flower. Okay, so here I will try to. So I will load the data set. Yeah, should work. So this is the data set. So each line is a flower, and you have some information about the flower, and you have the spaces. So you have 3 or 4 different spaces. And what we want to do is to project the data in order to find what are the individuals, the flowers that share the same characteristic. Okay. So here we use the PCA, Principal Component Analyzer. Okay. And okay, I don't want to explain all the code, I just want to execute it, and you have something like that. So you are able to separate by projecting in 2 principal components, you are able to do a separation. So here I'm using colors to identify what flowers is from what species, but in fact, here you can say immediately that there are something common here, and something common here. Here this is more difficult to interpret because you have there is no clear separation between the blue and the green species. Okay, so this is very simple algorithm that allows you to understand also patterns inside your data sets. If you want to do more elaborate stuff, you have to use non-linear mapping like the one that I will show you now. This is called the t-SNE algorithm. And this is something that has been added by one of the Indian guy that has done his Google Summer of Code. And I don't want to explain the math behind because it's, even for me, it's too complex to understand. So the short story is that I will do it with the, sorry about the, I will do it with that. So you have a data set like that. Okay, so very complex, something that is in an n dimension space. N maybe might be very, very big. And you want to project this in 2 dimensions. So if you use PCA, you will do a projection like that, but sometimes it doesn't work. So you have to do something more complex. So t-SNE is a probabilistic nonlinear algorithm. It means that sometimes you will have items inside the data set that will not be at but when you do the projection, they will not be close together, okay? So basically what the t-SNE algorithm is doing is, from that, you do something like that, okay? So you have something complex, and at the end, you obtain, yeah, something like that. So you project, and you project on 2 dimensions, okay? So very easy. Not that easy. So we implement this in Pharo. Atarva implements this in Pharo during his Google Summer of Code. and I can show you a short demo of how it works. Lawrence, if I find the, yeah, I know where is the code. The code is inside another, image. So here what we will do is that I will give to the algorithm, in fact, a grid. I will give it items that you can project on the grid like that. I will do something like that, and after that I will ask the algorithm to find the grid again, okay? So you have something like that. I don't know if you can see it. So, yeah. So it's a probabilistic algorithm, so every time you run it, you might have a different result. So you see here. So it's very fast, in fact. So at the beginning, maybe it's difficult to see, but at the beginning, everything is wrapped together. And at the end, we are able to separate the points. Okay? So this algorithm is also available on inside PolyMath. It's maybe at the moment the problem of this algorithm is that the performance is not really good. So when you want to do it on a data set with millions of elements, it doesn't work. Okay, so that's it for my demos. Just want to, okay, thank you. Just want now to try to, what we want to do in the future. First of all, I want to talk about a recent work that we have done with Conrad called Active Papers. So Conrad is not a computer scientist, he's a physicist, and he's interesting since a long time, but he uses a lot of computers, like all physicists, and he is interested to do reproducible research, okay? Because this is the major issue in science nowadays, to be able to reproduce what the people have done with computers. And this is not really easy. So what we have done is a small demo of putting together Pharo, JToolKit. If I remember, there was a presentation of JToolKit last year in Smalltalk's conference. So the tools that the people from Think have built. So we put together JToolKit, PolyMath, and we have introduced also more code, and we call Active Papers, in order to build a kind of scientific workbench. So I can show you, so it was present, there is a paper at last ESU conference. I can show you a short demo of this tool. Okay, I have a screenshot here. So basically, maybe it's better I do with a demo. Yeah, demo of Active Papers, yeah. So, interesting. Okay, I guess the demo will be out because I update my computer, my Mac to Catalina recently, and apparently it doesn't work. Yeah. Okay. Sorry. Yeah. Yeah, I didn't check this demo, and yeah. Don't upgrade your computer before a conference. It's not really good. Okay, so I just want to maybe just explain on the. I can. Yeah. It cannot be open. Yeah, sure. So maybe I will just explain here. Can do a demo later if you are interested during the conference. I will try to update this image. So we are using JToolKit in order to be able to have in the same document explanation, so text, simulations, and visualization. So something we want to be something similar to a notebook. So if you know about Jupyter, for example, this is something that is very popular among the scientists. And so here we have an example of these notebooks where we download the database of influenza illness in France. And from this database, we we do several operations on this database, and we are able to plot in fact, the number of people who are ill at the end, and you have the peak, epidemic peak that corresponds to the winter, in fact, in France. Okay. And what we want to do here is not, because usually in Jupyter notebooks, this is very linear. Okay, you have a text, you have simulation, you have code, and this is sometimes a little bit difficult, especially when you want to do reproducible research. The linear form doesn't work. So what we are able to do from that is that we are able to visualize this linear as a workflow, in fact. So in fact, we are able to see what kind of operation that we are doing on data and what you obtain at the end. So we build a workflow. So we are able, from the linear document, build a more elaborate workflows and be able to see how to reproduce the workflows in another computer. So this is the idea, the main idea. So this is the work in progress, and this is something very important for people who want to do science in notebooks, in fact. Okay, so another thing is that I tried, there are other software available, so I try to port. I'm working on the port of domains. I don't know if you know domains. So this is the work of Luciano Notafrancesco, who is, I say, YAAG, you know what is it? Yet another Argentinian guy, who is living actually in China, in Shenzhen. And we have exchanged a lot of emails. And he has done a computational algebra system in Quiz. And I was interested to port some of the, maybe not all because it's quite complex, some of the classes to Pharo. So this is an ongoing port. And the work he has done is very nice because there is a lot of tests. So it's very easy, more easy to port software like that from Quiz to Pharo. Okay, so there are also, don't have time here, but there are also a work from Massimo Notensini, who is an Italian guy who is working on formal, how would say, what is the name? Formal series. So the idea is to be able to express formal series in Pharo. So there are some work in progress about that. And at the end of ESUG 2000, so the last ESUG, we have also done some experiment with James Foster in order to run PolyMath on top of Gemstone, because he has done some work to run Pharo on top of Gemstone. So we tried to do it, but there was, well, okay, it's still it's very early at the moment. We have done some experiments, so we should work normally, but there are still some technical problems to solve. So you see, we are doing a lot of things, and my idea also is to combine also scientific computing and machine learning. There are new trends recently called scientific machine learning that try to combine both at the same time. The people in the Julia community, they are doing that, so I want to go in that direction. And I want to finish my talk by this slide. So we are looking for more support, we are looking for more contributors for the code, for the documentation, but you can also, so pull requests are welcome, but you can also try to contribute fundings to PolyMath. So I started a small experiment. I set up a sponsor GitHub page with a link here, so if you want to contribute, you can give a small amount of money to the project. And in order to have more fundings, I want to also to ask to be, in fact, part of the NumFocus initiative. So it's initiatives to find fundings for numerical software. So, for example, NumPy or Matplotlib, they are already supported by this initiative. So, yeah, so it's called NumFocus. Okay, so that's it for me. Thank you for your attention. Do you have any?
Yes. Is there any question? Yeah.
So in this call for collaboration, you are asking, is there any list of topics you are, I don't know, you would prefer something? Because I think it would be better if you can say, we don't have this, and would love to have some of that.
Yeah, in fact, the problem is that we have at the point that this is difficult to know what we have exactly, because we have lots of code. So so we are missing sometimes some functionalities, but yeah, we are missing the algebra part for sure. We are missing the everything related to data analysis, statistics, for example, something that we are missing. So we have, if you are going to the yeah, so we are the GitHub repository here. Yeah, so we have issues here, and some of the issues are missing stuff, in fact. So you can have a look to that. And we are also, I'm currently working on the book also to document everything. So the book is not yet available, but you can download a preview version of the book that explains everything inside. So yeah, it's difficult to give you an answer, because yes, there are some specific problems. I think the main problem here that we have is that because of the code base that has been done by lots of people, different people, there is a lot of difference in terms of yeah. So we need to clean the code, have more tests. Sometimes because of the diversity between the people, they don't use exactly the same API. So yeah, so the cleaning is an important part. It's not really fancy to do it, but this is something important.
Any other question? Okay, thank you. So now it's, yeah.
Thank you.